let's talk about the equations of lines. Particularly, I want to talk about lines in space. But to start, let's talk about lines in the plane, because it's always a good idea to start with something that's familiar. If I'm asked to find the equation of the line that passes through the points 2, 2 and 5, 6, I'm looking for the equation of that line. And just thinking back, I need to know a slope, which is a change in y over a change in x, so 4 over 3. But in this moment, I realize I actually found a vector. I didn't write it down like it was a vector, but if I thought about a vector that pointed from one point to the other here, right, the vector p1, p2, which I'm just going to call v, right? Well, I'd write it down in component form by finding the difference in the x's and the difference in the y's. And I could even think about drawing that vector in its standard position. And in fact, that vector v would be parallel to my line because it goes over 3 and up 4, and this line goes over 3 and up 4. Okay, so I have a vector parallel to a line. Maybe that'll help us in a minute. Right now, I should probably just finish finding the equation of this nice happy line in the plane. So I'm going to use this point and that slope. All right, just writing my line in its slope-intercept form. And there's the equation of that line. So I want to talk about lines in space. 2 points will still be enough to determine a straight line. If I have a point here and a point here closer to the camera, there's still only one straight line that goes between my fingers. The problem is there's not an easy way to describe the tilt of the line by using something like slope. Right here I have a rise over a run, right? When I have 2 components in this vector, there's just enough information to form a top and bottom of a fraction that describe the steepness of the line. If I think about doing this in space, and I thought about a vector that was parallel to my line, well, I'd have 3 things and I wouldn't be able to calculate something that was called its slope. But if I have a point on my line, and instead of slope I have a vector, I can still find an equation for the line. Let's look at that situation. Imagine that line L passes through a point I'm going to call P naught that has an ordered triple x naught, y naught, z naught. So line L passes through P naught and is parallel to a vector v. Where v has components v1, v2, v3. And I claim this is almost the same amount of information I had with my previous example in the plane. Right, because even if I had 2 points on the line, I could use those 2 points to generate this vector, this parallel to my line, just by thinking about the vector that pointed from P naught to P1, right, to the other point. So now I have a line in space that points from some P naught, that goes through some point P naught, and just happens to be parallel to some vector V. All right, let's imagine some other point on the line called P. And P can just be X, Y, Z, representing any arbitrary point on the line. So the point P is any point on the line. All right, well, I can think about a vector that goes from P naught to P, and I could actually write down components for that vector. that would be the vector x minus x naught, y minus y naught, z minus z naught. All right, so that vector also parallel to my line. Now it looks like it's on my line, right? But remember, equal vectors are vectors with the same direction and same length, so I could imagine moving that vector around as long as it still pointed up from left to right and was parallel to my line. Well, v is also parallel to my line, which means it has the same direction, where maybe it goes backwards because all I know is that it's parallel. Well, one nice thing about parallel vectors is I can make them equal if I rescale one. So I claim that p naught, the vector that points from p naught to p, is equal to some number t times the vector v. Right? If v was going in the right direction, it was just too short, I could multiply it by a number to stretch it to be the right length. If it was too long, I could multiply it by a number to squish it down. If v was parallel to my line but pointing in the wrong direction, I could just make that number t negative to flip that vector around and get it pointing in the correct direction. So right here, I have a nice vector equation that would describe those two vectors. So let's look at this equation. The vector p naught p is x minus x naught, y minus y naught, and z minus z naught. The vector tv, well, that's t times, well, let's go on distribute. T times the vector v would be tv1, tv2, tv3. Well, I have an equation that says those two vectors are equal. And the bigger claim was that p was any point on that line. So for any point p on that line, there is a number t that to make this equation work. Well, for these vectors to be equal, their components have to be equal. So x minus x naught has to equal tv1. Y minus y naught has to equal tv2, and z minus z naught has to equal tv3. Getting x, y, and z by themselves yields these equations. And these are what we call parametric equations for that line. Parametric equations for that line L. You put in a value of t, and you get an ordered pair on that line. The idea being, if we start at x naught, y naught, z naught, and we add some multiple of v1, v2, v3 to them respectively, we simply get a point that's sliding up or down the line. One thing about parametric equations, it's always a good idea to let your reader know what parameter interval. To get the whole line, we need every possible real number for t. All right, so now these are equations that generate that line, parametric equations. This works in the plane too. We found the equation of a line in slope-intercept form. Had we been asked for parametric equations for that line, we could have written them down like this, right? X naught, 5, y naught, 6, plus v t, v1t, plus v2t. Right, and here I could just be thinking about this in the xy plane, like z is 0, so I have a z equals 0 here. This is a set of parametric equations that generates that line. And you can actually pause the video here and check that by eliminating the parameter. Solve this equation for t, plug it into this one, and make sure you got the equation I just erased. That this actually works for lines in the plane as well as lines in space. So now we have parametric equations for lines in space. We can actually write this down in a vector form too. The vector equation for lines in space. EQN for equation, run out of space here, but I should put the R on vector. The vector equation for lines in space. The vector R of t is equal to R naught plus t times v. Well, I know where the t times v comes from, right? That's this vector. R naught is what we call a position vector. R naught is the vector that points at P naught. So it's this vector. What this vector R does, every time you plug in a t, it gives you a vector that points to a point on the line. It itself is what we call a position vector. All right, so let's do an example. I want to find a set of parametric equations and a vector equation of a line passing through 2 points in space. All right. Find parametric equations and a vector equation for the line passing through 1, 0, 3 and 2, 6, 1. So 2 nice points to deal with. And all I have to do is find those 2 lines. Well, now I need to play that game like I played in the plane. What do I need to know? Right, for points in the plane, I always think I need a point and a slope. But what we know now is for lines in space and even lines in the plane, what we really need is a point on the line, which we're good, we have 2. I'm going to use this one in a moment because I'm lazy and things with 0 in them make things a little easier, so that's going to be my choice for P naught. And I need a vector parallel to my line. Well, I find that vector just by finding the vector that goes between these 2 points. And that would be the vector 1, 6, minus 2. Okay, so I have everything I need to write down the parametric equations for this line. X naught plus TV1. Y naught. Probably wouldn't even usually write that 0 down. Plus 6t plus z naught. Excuse me, z equals z naught plus minus 2t. And I want the whole line, so I need t to be between minus infinity and positive infinity. If I replace my minus infinity and positive infinity with numbers instead of a line, I'd get a line segment. Let's talk about that in a minute. For now, I want to write down a vector equation, which if I think about it in the format stated previously, it would be R naught, the vector pointing at that point, plus t times this vector. And I could write this down in the IJK format, but there's my nice happy vector equation, also for all the possible values of t. Okay, so let's think about this set of parametric equations, or this or this vector equation, but just when t is between 0 and 1. Okay, well, if I let that happen, when I plug t equals 0 in, I get P naught, 1, 0, 3. If I plug in a 1, I get the second point I had there. Because what we did is actually set it up so that between 0 and 1, we start at this point and end at that point. If I thought about the line segment between 0 and 2, well, I'd get a line segment that looked a lot like that one, but was twice as long. If I make this interval be between minus 1 and 0, and now I have a line that stops at P naught and starts on the other side. And so that's the difference between a line and a line segment.